So for this problem here, they want us to give them the values of t at all the critical points. But for a critical point, we need a derivative. And for a derivative, we want dy over dx. So notice that dy dx is actually equal to this here, because dy dt divided by dx dt, instead of dividing fractions, we can multiply. But you have to take the second fraction and reciprocate it. So you keep this first fraction the same, you turn this upside down, and now these dt's knock out. So the point is, to find the derivative of this function, go dy dt and divide it by dx dt. So dy dt is the derivative of this with respect to t, so that's what you get with the chain rule. The derivative of x would be this here, and now we want to go dy dt divided by dx dt. And so here is our derivative. Fully cleaned up, this here is dy dx. We have negative 2/3 times this fraction. Now remember, for a critical point, that's where the derivative is either 0 or undefined. And here we have opportunities for the derivative to be 0 or undefined because you have a fraction. Anything that makes the top 0 or that makes the bottom 0. And those two things combined constitute the critical numbers. So set the top equal to 0. Set the numerator equal to 0, and now we have to think about this equation. I want to write this down again, but I want to leave the parentheses empty. So cosine of something is 0. I always think of the unit circle. It always helps me. Think of the unit circle like this. And remember that cosine is really just the x coordinate. So I want my x coordinates to be 0. That happens here, and that happens here, only there. Because this point has an x coordinate 0, and so does this point. But what exactly is the angle there? That angle is pi over 2. If you open up your pre-calc book, that's pi over 2, and that's 3 pi over 2. So if I take 1 pi over 2 and plug it in there, cosine of pi over 2 is 0. Or I can take 3 pi over 2, plug it in there, and it's going to be 0. So here's what I'm trying to say. 1 pi over 2, 3 pi over 2, like 1, and then you skip 2 and you go 3. Skip 4 and then you go 5. Skip 6 and you go 7. Skip 8, you go 9. So what I'm trying to say is that an odd pi over 2, 5 pi over 2, 7 pi over 2, 9 pi over 2, any odd pi over 2, any of these numbers, angles, will satisfy this equation. Now think about what yours says. Yours doesn't, it's not blank, it says 2 times that thingy. Is we can divide all of these by 2. We can divide all of these by 2, and we can simplify them to get these guys. And the reason we can divide all these guys by 2 is because if you take, for example, this number and plug it in there for t, that 2, the first thing it does is it knocks out the denominator. And all that's left is the original number that makes cosine 0. You see what I'm saying? So all of these guys here, if you take any one of these and you plug it in there for t, the 2 will simplify with the denominator and you'll get back the original values that make cosine 0. So what I'm saying is all of these guys, these are critical numbers that work for there. But the problem is that if you read in the directions, it said that the t that you use has to go from 1 pi over 12 all the way to 24 pi. That says 24 pi over 12 at the end, because 24 pi over 12 is just 2 pi. So really this goes from like 0 all the way to 2 pi. Now, not all of these work, only some of these. So the question is, these guys that worked, which one of these are these? Well, it's not that obvious because all of these denominators, if you look carefully, look, let me even focus my camera. If you look at all of these denominators, these are all denominators of 12. So what you can do is you can rewrite all of these fractions as 12 in the bottom by multiplying top and bottom by 3. So if you look here, if t equals this or that or that or that, any one of these guys plugged in for t in the numerator is going to make that numerator 0, which means the derivative is 0, which means all of these guys are critical points. But some of these aren't good. Like for instance, this one's trash because that's 27 and the cutoff is at 24. So this one's no good. So you got to make sure that the things that you turn into the teacher are things that are found in here. And yeah, I know that a lot of these can be reduced, but I left them all with 12 in the bottom just to make it clear what they are. So for now, for sure, these guys are part of the set. But these guys are the ones that make the top 0. Now we have to discuss the denominator, which is sine of 3t. So now looking down here, We want sine of 3t to be 0. So I think of it as sine empty equals 0. And now think of the unit circle. And remember that sine on the unit circle, that's like the y coordinate. So where on the unit circle do you have a y coordinate of 0? Right here and right there. Where this is 0 and this is pi. And you can think of it as like 0 pi, 1 pi, 2 pi, 3 pi, 4 pi, 5 pi, and so on and so on. So this is like 0 or 2 pi or 4 pi or 6 pi, any even pi. And this is 1 pi, 3 pi, 5 pi, any odd pi. And really, so it's basically just like 0, 0 pi, 1 pi, 2 pi, 3. You're just counting. Just count like a baby would count, but you attach a pi. And so on and so forth, forever and ever and ever. Any one of these guys plugged into here, the sign of that would be 0. So what you do is you divide all of these guys by the number 3, and so on and so forth. So all of these guys would work because all of these plugged into your denominator up here, all of these plugged into there would create a 0 on the bottom, and a 0 on the bottom means that the derivative is undefined, which makes it a critical point. But now the question is, these ones coincide with which of these? I don't know, because these have denominators of 3, and I wish to see denominators of 12. So let's rewrite all of these with denominators of 12. So as it turns out, this was actually a perfect place to stop at the 6 pi, because the 6 pi over 3 became the 24 pi over 12, and that actually is the cutoff. So if I had kept counting to like 7 pi, and then 7 pi over 3, that would have become like 28 pi over 12, and that would have been no good because that would have been bigger or beyond the 24 pi over 12. So that would have been no good. So as is, we have the values of t here and here. So this here should be the complete list of the t values at all the critical points of the original function, where I believe this first portion here came from these guys, but I reduced them. And these are the things that made the numerator of the derivative 0. And these here in the back, these are the reduced versions of these guys down here, where these values are the numbers that make the denominator of the derivative 0, so the undefined values. So again, all together, these should be it right there. Now let me show you something kind of cool. So the proposition is that these first values are where the derivative is 0, and these back values are where the derivative is undefined. So let me just randomly pick like 5 pi over 4. Let me take 5 pi over 4 and plug it in for t here into the graph. So this is what you type in box 1 to make the image. And in box 2, I typed in the same thing, but instead of a, I'm gonna type in t. What did we say? We said we're gonna test 5 pi over 4. Watch what happens here. If I plug in 5 pi over 4, 5, let me spell pi, let me divide by 4, and look at what happens. You get this point here, which is right there. And you notice that here, the tangent is gonna be perfectly flat because the slope should be 0, because this 5 pi over 4 is what made the derivative 0. What about one of these guys? These are where the derivative is undefined. So for example, how about we test 5 pi over 3? Let me go back here and let me plug in 5 pi over 3. So instead of 5 pi over 4, let me change it to 5 pi over 3 and watch what happens. Now you have this point down here, where if you draw the tangent line that you draw is gonna be perfectly vertical up and down, because a vertical line has a slope that is undefined, as it should be, because that 5 pi over 3 was an undefined value, because 5 pi over 3 made this denominator 0, and when the denominator is 0, your derivative is undefined. Now for the second part of this problem, they want us to tell them the slopes of the point in the first quadrant where the graph crosses itself. So you can clearly see that the orange in the first quadrant, it crosses itself right there and there. You see that? So I need to know what that point is right here in the first quadrant. So what I did here is, so that's the original function. And then I typed it in again, but I created slider A. Slider A is there. So what I did is I let slider A be k pi over 12, where k is like 1, 2, 3, 4, 5, 6, 7, 8, all the way to 24. And you can see it's actually counting by 1. So if I just zoom out, what we have to keep an eye on is we have to pause it whenever the purple point is right here. So I can actually drag it around, watch. So this is saying if I drag it to 1, that's what I really want right there. So when k is 1, and look, if I drag it manually, it wraps around, and it works again, boom, right there, when k is 17. So when k is 17, and then when k is 1, that's when the magic happens, 1 and 17. So here's what this is saying. When k is 1, t equals 1 pi over 12. And then when k is 17, t equals 17 pi over 12. Let's pretend that t is pi over 12. Plug in pi over 12 there and there. So when you take pi over 12 and plug it in for t there and there, it simplifies to this point. This is a point on the xy axis. Now let's do this again, but for t is 17 pi over 12. And notice what happens. If t is pi over 12 or 17 pi over 12, when you take those values and plug them into the function, you actually get the same xy ordered pair, which is why at these two locations, the graph crossed itself. If you had plugged in anybody else in the list, you would not have gotten these exact values. And these are good because these were in quadrant 1, and that's the only time the graph crosses itself in quadrant 1, at these two values for t. But then remember what they wanted. They didn't want the locations per se, they wanted the slopes. Read the directions. They wanted the slopes at these values. And so what we do is we go here to our derivative. That was the derivative which spits out slopes. So to finish this problem, take pi over 12 and plug it in to t. Take 17 pi over 12 and plug it in there. And this is what we should actually get in conclusion, that when t is pi 12ths, the slope is this here. And when t is 17 pi 12ths, that's our slope. It's appropriate that one of the slopes is positive and one of them is negative, because visually, if you look at the graph, here at that point in purple, one of the tangent lines has a positive slope and the other has a negative.